Mahavidyalaya, Latur. Then I would like to thank Professor Parke sir, Professor Momin sir, all these colleagues, and all those who are contributing for arranging this conference. Thanks, and you are here to listen us patiently. And maybe you scold outside, going outside to us, it's fine, but you have to hear, you don't have any choice, whatever. I would like to come here. When I was in Germany, I read one newspaper. There was one sentence, one of the hero, he had a drug condition, he beat his girlfriend. Then, sometimes before I read some news from film industry. One of the hero, big hero, he smokes 12 cigarette packets in a day. Then I read one newspaper, then I heard one hero, he did 3 marriages. Now, you think who is your hero? We have to choose our hero cautiously. This is the most important thing in our life. If we are in juggling, which is our hero, who is drinking alcohol, who is taking 12 cigarette packets a day, who is beating his girlfriend, they are our heroes, or these are our heroes. The person where we don't have any educational system, at that time, Mahatma Phule, he brought education to us. For girls, his wife, for us, he is one of the heroes. If we choose him as a hero and follow his all instructions and all those things, you will become a nice person, or you will become a big researcher or big industrialist. This is, I think so. Then I would like to come Rajarshi Sharma Maharaj, who is from Chhatrapati, and you are also studying in the same college with his name. He is also our hero. When we have caste systems, at that time he tried to break all caste systems and make education to poor, and each caste. Making hostels, that means he put like this for us. Then my third hero is Mama Dr. Babasaheb Ambedkar, because he brought the legacy of these two persons forward, and he impacted whole India, not only for Maharashtra, for education. He brought education to poorest to poor person. ज्यांना कोणाला आपलं स्वतःचं अस्तित्व नाही असं वाटत होतं, अशा लोकांसाठी त्यांनी शिक्षणाची गंगा आणली. ती आपल्या राज्यघटनेच्या माध्यमातून आणली, त्यासाठी स्ट्रगल केला. Second thing, what he did, he read daily or he studied daily 18 hours. This is the most important thing for us. Only going to film, mall, this is not our. You can enjoy mall, film, that is also important, because you can get things from there also. But you have to read, because this life will not come again and again. We are on this planet for only one time. Whatever your religion tells, I don't know. But I know this is first life and last life for us. That's why you have to use your life for your betterment, for your family betterment, for your society, and ultimately for our country, and lastly for human being. This should be our motto. Now, the legacy which Mahatma Phule gives, the legacy which Sharma Maharaj gives, or the legacy which Dr. Babasaheb Ambedkar gives, that legacy, किंवा ती काही जी आपली परंपरा आहे ती पुढे चालवण्याचं काम आपल्या महाविद्यालयाचे अध्यक्ष डॉक्टर गोपालजी पाटील साहेब हे पुढे चालवतात. आज गणिताचा दिवस मुलगा सुद्धा येऊन तुमच्या कॉलेजमध्ये बी शिकू शकतो. तुम्हाला अकॅडमिक स्टेटस मराठवाड्यात मला वाटतं फक्त शाहू महाविद्यालयाचा अकॅडमिक स्टेटस आहे. की जे काही युनिव्हर्सिटीला जाऊन तुम्हाला डिग्री घ्यावी लागते ती डिग्री तुम्हाला शाहू महाविद्यालयाच्या नावाने मिळते. आणि तुम्ही काय पाहिलं असेल मी काही नव्हतो की ही इज अ 92 years boy. ओके, व्हॉट इज हिज एनर्जी? आपण 25 नाही तर अजून 22-23 मध्ये माझं पाय तुटलं, माझा हात दुखलं, माझी पाठ दुखली, माझं पोट दुखलं, मला बोर झालं, मला दमना झालंय, मला दोस्त नाही, माझी मैत्री पळून गेली दुसऱ्यासोबत, मी काय करू, मी कसं जगू का नाही, हे आपले प्रश्न असतात. आणि इफ यू लुक this hero, he is constantly working from now last 92 years in this society. He brought education to us. And right now we are getting education from this one. That's why please never become bold in your life. तुम्ही कधी आळशी बोलू नका. स्वतःला खूप बोल झालं सांगू नका. तुम्ही पुस्तकं वाचत जा. थोडा मोठ्याची आपला जीवन तुम्ही निवडा. You can choose your hero. What does it mean? छत्रपती शिवाजी महाराज, छत्रपती संभाजी महाराज, डॉक्टर बाबासाहेब आंबेडकर, महात्मा फुले. What do you want? You choose those heroes, not the hero who is drinking, who is smoking, who is going into jail. Those are not our heroes. This is my clear-cut message to you. Now, what is research? Research is not a job. It is a human activity. That means if I am coming to college, I am working 8 hours and going to home. Or if I am going to institute, working 8 hours, going to home. This is not the research. Sorry, this is not the research. It is a routine job. But research is not a job. If sir told this green chemistry, he has to think 24 hours. Green, then comes little bit outside. If we are thinking only 8 hours, go to university, teach students and go home, it is not like this. If those who are want to come to research, they have to read, write. This is the most important thing, and you can do that. You have much more energy. Because if a 92 years boy, what बाबासाहेब आंबेडकर told, जो कोणी शिक्षण घेईल, शिक्षण हे वाघिणीचं दूध आहे, जो कोणी ते शिक्षण घेईल तो ढळकाळेल. आणि काल तुम्ही वाद बघितला 92 वर्षाचा आहे का नाही? मग ते जर त्या 92 वर्षाला इतके मेहनत घेतात, आपण तर 22-23 गावातून बसणार ते थकून गेलं वाटतं. तर हे तुमच्या यायला नको. तुम्ही त्यांना आदर्श माना. तुम्ही तुमचा जो काही आदर्श असेल तुम्ही जा, मागच्या पुस्तकामध्ये जा, आपल्या सोसायटीमध्ये जा. आणि शेवटी आय वुड लाईक टू ब्रिंग टू युअर नोटीस, यू मेक युअर मदर युअर आदर्श. उद्या बेटर आपण 9 वाजता उठतो. खूप थकलो होतो. काल पिक्चर बघितला, 12:30 आलो, दोस्तासोबत गप्पा मारल्या आणि सकाळी 9 वाजता उठतो. आपली आई 4:30 वाजता उठते, 6:30 करते, तुम्हाला नाश्ता देते, पुन्हा धुणं भांडी करते, पुन्हा जेवण बनवते, पुन्हा दिवसभर पाकडणं, झाडणं, पुसणं हे सगळं करते. पुन्हा संध्याकाळी तुमच्या वडिलांचं, तुमच्या बहिणीचं जेवण बनवते आणि ती संध्याकाळी 11 वाजता बेडवर जाते. म्हणजे जी बाई पहाटे 4 पासून 11 पण काम करते ती आपल्या डोळ्यापुढे आहे आणि आपण तिला आदर्श न मानता कुठेतरी पिक्चरमध्ये बघून आपण आपला आदर्श शोधतो. ते चुकीचं आहे. माझं मत आहे तुम्ही तुमच्या आईला आदर्श म्हणा. ती बघा पहाटे 4 ते 11 किती काम करते आणि आपण किती काम करतो. तर त्यामुळं तुम्ही आईसोबत पहाटे 4 वाजता उठा, संध्याकाळी 11 वाजता झोपा. तुम्हाला काही तुमच्या आयुष्यात कमी पडणार नाही, पैसा कमी पडणार नाही, तुम्हाला मान कमी पडणार नाही, तुमची इज्जत कमी होणार नाही. प्लीज फॉलो युअर मदर. दॅट विल बी द बेस्ट इन्स्पिरेशन इन अवर लाईफ. Now, I would like to talk about outline of supramolecular interaction, role of various non-covalent interactions. All these things you are studying from 7th class, 8th class. I am not talking something extraordinary. Just I am talking what we are learning or what we learned from last 10 years. Now, what is non-covalent interactions? We are talking about you are making your compounds in your laboratory, ABC, BC, you are preparing some derivatives, and from those compounds you are making some derivatives and taking their melting point and all these things. Those compounds we are preparing by covalent interactions. And now, for having a covalent interaction, we need this much energy in kilojoule per mole to make a covalent bond. But to make a non-covalent interaction, we need this much energy. That means the energy needed for covalent bonding is more than that of the energy needed for the non-covalent bond. This is a simple thing. Now, supramolecular chemistry is not a hi-fi chemistry, something is there. It is present in the nature from the beginning of the life. Because if we go and see our plant, there are leaves. In those leaves, photosystem is there, and that photosystem produces food corpus. And that is the photosystem which is present in that leaves are again phosphate, and all those things. and those things are non-covalently bonded in that one. That means those things are non-covalently bonded. That's why it is already present in the nature. Just we are copying and we are trying to copy the things and we want to make in the laboratory. Now, these are the non-covalent interactions which we can use in laboratory to make the supramolecular self-assembled material. First is electrostatic interaction, dipole-dipole interaction, dipole-ion interaction, again coordinate bonding, and further van der Waals interaction, pi interaction, hydrogen bonding. Now, we know that again positive, negative, they attach with each other. Positive, repel from each other. Negative, repel from each other. These things we are learning from beginning. But we have to use these things in our supramolecular chemistry or in our further study. And there is ample of scope for the application of these interactions. Here, if we look and see, there are positive charge, negative charge, Q1, Q2. These are the charges for this positive and negative. And if we put this K constant and R square is the distance between Q1 Q2, then this F force of attraction between two ions, positive and negative, it is calculated by this formula and this Coulomb's equation, and C again stands for the constant. Here the K is equal to 1 by 4 pi epsilon naught. Epsilon naught is equal to 8.85 into 10 raised to minus 12 Faraday per meter. You don't do all these calculations and simple thing, positive and negative interaction takes place, and those interactions are called charge-charge interaction, and those interactions are also available in the nature, available in our body also, and we have to use those interactions for our study. Then comes if the positive and negative charge is not in vacuum, if these are in air, then the force between these two ions are different than that first one, and here F is equal to K into Q1 Q2 upon epsilon R square. Here epsilon is again 1 in vacuum or in air, but epsilon is equal to 1 to 10 in a non-polar organic solvents, whereas epsilon is equal to 17 in water. That means this again depends on this epsilon, again F changes. And when epsilon changes, when we go from vacuum to air, or if there is an intermediate between two charges, suppose solvent, then this changes, F changes, or force of attraction between positive and negative charge changes. And these are the natural systems. Suppose here if we take lysine segment and this is a glutamic acid segment, then we know that the positive charge resides on this ammonia, whereas the positive solvent, whereas the positive and negative charge on this carbon, and they interact with each other, and the energy required for this interaction is equal to again K into Q1 Q2 upon epsilon R. Here, if we look, this is an example. In this case, two peptide chains, they are connected with each other, and synthesizing such complex molecules is very difficult. In this case, this arginine, it has this dotted group with positive charge, and if we put the phosphonate segment in this phosphonate negative, it interacts with the positive charge. At the same time, this phosphonate negative also interacts with the positive. At the same, and this makes us complex entity, and this is possible to do this non-covalent interaction. Synthesizing such covalent bond is really difficult. That's why we can go for such type of interactions. Now, not only charge-charge interaction takes place, again, here dipole-ion interaction also takes place. We know that if we take example of HCl, there positive charge is present on hydrogen, or delta positive charge is present on hydrogen, delta negative on nitrogen. Then here, if we have anion in our system, anion interacts with the delta positive of this polar molecule. At the same time, if we take cation, this cation interacts with the delta negative of this molecule. And such type of interactions are also present, or we can use such type of interaction in making supramolecular self-assembled material. Here again, E is proportional to R, inversely proportional to R square, and here again if we take our example sodium chloride, if we put in water, then the delta negative oxygen interacts with the sodium molecule. Now, we can use such system. If we look this molecule, this is the NDI molecule. Here, in this NDI molecule, there are 4 carbonyl groups, and we know that carbonyl oxygen, it pulls electron towards it. When it pulls electron towards, then at that time, what happens in the core? Here, electron deficiency is related. when electron deficiency created here, then it makes a polar system, or that induction of dipole takes place. And here, that means delta negative or delta positive. So here is more electronic present, or electronic environment is present than that of the core. And when this molecule incorporated in the liquid bilayer membrane and studied for fluid ion transportation, they observed that here Cl negative, it interacts with this positive and it moves across a liquid bilayer membrane. If you go, yesterday I think Srinath talk about the sodium meter, sodium ion, potassium ion and all those things. That means in our body, the sodium ion channel, potassium ion channel, these channels are present. And such channels one can produce in laboratory by using such system where one can use such molecules, put it in liquid bilayer membrane, and then study about the transportation of Cl ion across the liquid bilayer membrane. Such type of dipole-dipole interactions are also present. Again, dipole-dipole interactions. In this case, two molecules having a dipole. Here, if you look this one, delta negative, delta positive. When it attracts with the other, delta positive, delta negative. And if you look HCl, in this HCl, again delta negative project on Cl, it interacts with this H. And again, the energy needed for this one is less than the place because it is proportional to the output. Now, a real example, if you look, this is a ethanol we are using in our laboratory. Then butylbromide we are using in our laboratory. Here, delta negative positive is present on this proton or hydrogen, and delta negative present on this oxygen. At the same time, delta positive negative present on bromine and delta positive on this carbon. They interact with each other via dipole-dipole interaction because we know that delta positive interacts with the delta negative. Madam, don't know. Again, here if you took acetone, in this acetone we know that this carbonyl liquid again pulls electron towards each. When it pulls electron towards each, at the same time, look, this delta positive, delta negative, and same type of dipole-dipole interaction takes place in this system. Now, from beginning or from 8th, 9th class, we know that 5 bonds they repel from each other. We are always studying. If this 5 bond is present in the system, and if we take another 5 bond system, then if we bring together, they repel from each other. Is it possible to make attract towards each other? Yes, answer is yes. What people are doing, they are putting such type of cation. If you look in this case, here is a cation. When you put such cation with this benzene nucleus, what happens? The electrons which are present in their system or in benzene nucleus, those are moving towards the cation. When it pulls towards the cation, at that time, here delta positive charge is created at this side. Then this cation induces dipole in the benzene nucleus, and here this here becomes delta positive, negative, this here becomes delta positive, and then cation. Then it is again the cation pi interaction. If we think reverse way, if we put negative ion, then in that case what happens? It repels. When it repels, then positive charge goes to the other side. Like this, one can see cation pi interaction as well as anion pi interaction. Now, if you look this one, here simple example, this charge NH3 positive. This NH3 positive, if we put this fluorine here, it pulls electron from this fluorine and delta negative resides this side, delta positive resides this side, and what happens? Then this cation pi interaction takes place. At the same time, if we put the polar, this dipole, already dipole, molecule having a dipole. When we put this molecule with this fluorine here, what happens? These two protons, it has delta positive charge. When it has delta positive charge, those positive charges pull the electron system towards them. At the same time, delta positive here. And then this is the dipole induced dipole interaction happens. Again, these are the calculations. It is not that much necessary to go through them in detail. But one can see simple molecule, put it cation, one can make induction of dipole in benzene nucleus, put it anion or this dipole molecule, we can make again the dipole, or we can induce the dipole in the benzene nucleus. Such type of interaction we can generate in laboratory. I told pi they repel from each other. What happens? we know that if we draw benzene nucleus here, this double bond is here, this double bond is here, this double bond is here. These are double bonds of the pi electrons. But we can rewrite this one as double bond here, double bond here, double bond here. But it says this electronic moment, that means these pi electrons, they are rotating inside the. When they are rotating inside the benzene nucleus, a stage will come when most of the electrons they go at one end. When they go at one end, suppose look this one. When these electrons, pi electrons are rotating, we are saying this is an electronic rotation. The electrons goes towards this one. Then delta negative charge induction takes place. At the same time, delta positive charge induction takes place at the other end. That means without putting any cation or dipole moment, dipole molecule, we can make a molecule as a, or we can induce the, it automatically induces dipole in itself. When this dipole induction takes place in the molecule, at the same time, another molecule which has delta positive and delta negative in the same system that interacts with this one, then due to this pi-pi interaction happens. We are feeling, from beginning we are feeling there is no pi-pi interaction takes place. Pi-pi repeats. But due to this moment of electron, a stage will come when this delta negative and delta positive charges induction takes place. When this induction takes place, at that time, another molecule having the opposite charges, they come towards each other and making the pi. And such type of interaction is called as, again, induced dipole interaction. And here, one can, again, here says, when two such molecules come here close to one another, these fluctuating dipoles. That means these dipoles are not permanent ones. These are the fluctuating ones, and such type of interaction takes place. If we look this benzene, again here the distance between these two is 3.4 electron, and this nucleic acid in this also. If we go here, we again see ATGC pairs are present in our DNA and all. There is pi stacking takes place between the nucleobases. Such type of interaction, again sandwich state, again T-shape, earlier displacement, such type of interaction takes place in the system. Then one can use such interaction because they are synthesizing such clump molecule and they incorporate or here this C60 molecule, fluid molecule, it interacts with such complex clump and make an interaction. Due to pi interaction, because there is no positive charge, no negative charge, there are no charges are present, that's why it can do via pi interaction. Then comes van der Waals interaction, again it is the interaction between two molecules or two charges. This is that means the net results of attraction and repulsion, and this is called as a van der Waals interaction. When it takes place, when the distance between two atoms is greater than 0.6 nanometer, then the force are extremely weak. That means if the distance between these two molecular systems is greater than 0.6, this van der Waals interaction does not occur. But when it is 0.6 to 0.4 nanometer, then such type of interaction can occur. Then again, if this interaction is smaller, then again repulsion takes place. That's why van der Waals interaction does not happen. Now again, these are the calculations how van der Waals interaction takes place. This is the plot diagram. How these are the van der Waals react, they interact with each other, at what energy they taking such type of interaction, at what energy they showing the repulsion material. This diagram. Now, hydrogen bonding, this is one of the most important phenomena in supermolecular chemistry, because here in hydrogen bonding we say the hydrogen which is present on electronegative atom, it interacts with the another electronegative atom. This is a non-covalent bonding. And here, if you look this your periodic table, partial periodic table, here these are the electronegative of this nitrogen oxygen fluoride ClBr. If the hydrogen is present on these electronegative atoms, then it interacts with another electronegative atom and make the hydrogen bonding. Again, here not only these atoms size also makes impact on the hydrogen bonding. Here, the hydrogen which is present on the electronegative atom is called a hydrogen donor, and the electronegative atom which takes this hydrogen is called as an acceptor. And here such type of interactions are present, and the distance between these two molecular system should be this much. If hydrogen is present on oxygen and it interacts with this oxygen, this should be the distance between two. And if hydrogen is present on nitrogen and it interacts with this oxygen, then again 2.9 angstrom plus minus 0.1. And if hydrogen is present on nitrogen, then it interacts with carbonate, then such type of distance is maintained by the system. And thus, this two system, that is the last but the two, those are the most important in natural systems. Again, we know that GCPL, this happens due to hydrogen bonding, and due to hydrogen bonding in peptide chain, this is again group. Hydrogen is present on electronegativity atom and interacts with the another one. And again, amino acids and water network. Also, this is the alpha helical secondary structure, and if we look this stability of this molecular system, then these hydrogen bondings are more important to stabilize this system in the nature. And again comes coordinate bonding, those who are emerging students, they know better than me what is in the coordinate bonding. And here, if you do this ammonia and BF3, it makes a coordinate system. And such type of interactions are also important in the supramolecular chemistry. Why we are taking all these basics? Because it is employed in the supramolecular chemistry. But if for supramolecular chemistry, we can make a nanometer from supramolecules, and we can use those supramolecules for different applications, for different applications as well as drug delivery or gene delivery. And this is natural system. Just I talk about this hemoglobin or chlorophyll. Here, this heme which is present in this enzymatic system, it interacts with this histidine residue via the coordinate bonding. Now, these are the dependence of energy on distance, and this is a model how this charge interaction takes place, charge dipole interaction, dipole interaction, charge inducible dipole interaction, dipole inducible dipole interaction, and dispersion, van der Waals interaction, hydrogen bonding, and the examples and the dispersions. Now, concept non-covalent interactions are fundamentally electrostatic in nature and can be described by Coulomb's law. And the delta positive, the partial positive charge, delta negative, partial negative charge. Now, again question arises, which one is the most stronger in non-covalent interactions? If we look, charge interaction, the approximate energy is 13 to 17 kilojoule per mole in water, whereas for hydrogen bonding, 2 to 21 kilojoule per mole in water. Again, van der Waals interaction 0.4 to 0.8. That means one can say charge interaction is stronger as compared to hydrogen bonding, and these two are the stronger than that of van der Waals interaction. This is the basic form these things. Now, water, it is the most important things in our life, because without water we can't live, without water we can't alive, and it makes 70% of every living things body, and that's why it is most important, and it directly influences the strength of most of the non-covalent interactions. That means those interactions which we are already present in nature, those interactions takes place in the medium of water, because there is no alcohol, we are not putting benzene in, then also this type of interaction takes place, and this is their water effects much more on those type of interactions. If you look these, again, the hydrogen which is present on carbon, nitrogen, and oxygen and sulfur, here one can see H2O, it exhibits how it shows the property, and those properties are unit 1. Molecular weight 18.0 to 20.0, then boiling point plus 100, and heat of deposition 14.71 kilojoule per mole. And the hydrogen which is present on oxygen, it shows different properties than that of the carbon and nitrogen and sulfur. Now, water, what it shows? Water shows hydrogen bonding, because we already told hydrogen atoms which are present on electronegative atom, it shows the interaction with the other electronegative atom. Here, if you look this, again I told here, the oxygen, it has these two hydrogens, and that's why we can say this is a donor type system. And delta negative charge is present on this oxygen, that's why it is the acceptor side of this molecule. And if we go in nature, all people are studying in ice, one water molecule interacts with the whole water molecule, whereas in liquid water it interacts with the free water molecule. That's why water is most important. It shows different type of behavior. If we study water in detail, one can take Nobel Prize if we remain on goal. Here, I am talking about it shows in ice full water molecule. People are showing 5, 6 also in crystal form of the water. If we go that condition or that level, then it is very tricky. And always read water, you will get. आपण म्हणतो ना, पाणी हे खूप मित्र असतं, पाणी हे खूप छान असतं, पाण्यामुळे जीवन पवित्र असतं. तुम्ही जर पाण्याचा अभ्यास केला खूप काही तुम्हाला त्यातून मिळेल. That's why learn about water, learn about, read about water. It will do lot of things to you in your life to be research. Now, if we look, we know that आपले सकाळी उठते, मीठ पाण्यात घालते, भाजी घालते, त्यावेळेस हा मीठ पाण्यामध्ये मिळत करतो. तर काय म्हणतो पुन्हा आपण आठवीपासून शिकलो की this sodium, this Cl negative, it reacts with this oxygen of the, hydrogen of the water. At the same time, the positive charge, sodium positive, it reacts with the oxygen of the water, and that's why it oxidizes. If you look this molecule here in this case, there is no water present. Then this structure is charged by the hydrogen bonding. That means this structure is charged by the hydrogen bonding. If we put water, what happens in this system? If we have water in this system, then this water starts to make hydrogen bonding with the hydrogen which are present in this system or this enzyme. When it makes hydrogen bonding, at that time, this interaction it breaks, dissociates. When this interaction dissociates and it makes interaction with this molecule, then disturbance will take place. Such type of effect is happening in system or in natural system. If we go and do Google it, I took this figure from Google, and here one can say if we put water, methane in water, then this water makes this liquid structure around the methane, because water does not exist with the methane. Methane is hydrophobic, water is hydrophilic, and hydrophobic does not come to us. In that case, water makes liquid around the methane, and it shows the such type of structure in the system. Now again, pH also plays an important role in supramolecular chemistry. I think in 11th, 12th class we already studied about pH, pOH, pKa, pKa, pKb, all these things. That's why pH is also important. I always ask students whenever मला जेव्हा तेव्हा वाटतं की मुलांना काहीतरी एक सहज प्रश्न विचारतो, सहज त्यांना विचारतो व्हॉट इज द पीके, ते सांगून देतात 7. If we have 7 pKa water, then it is really difficult. That's why Google read what is the pKa of water. I like this question always, and we always forget this answer. Okay, pKa of water always. Now pH, we know that this formula. Then again, what is the use of pH in natural system? In natural system, we take this one enzyme. At different pH, it has different environment. If we look pH 7, it has this blue one. This is the positive charge on this enzyme, and this red one negative charge on this enzyme. If we go further pH 8, then this negative charge starts to increase, because we are increasing basicity. When we increasing basicity, then it increases. And if we go to the right and till pH 11, then this enzyme completely it has, because we have positive charge in that, and this surrounding pH it makes it negative. And if we go down, then we can see at pH 4, this is the positive charge and this is the negative charge. And at the isolated point here, one can see at pH 7, this is the 6.8 pKa. And this surface is, one can see at intermediate, and then this is the positive, this is the negative. That means pH affects, simple answer, pH affects on the environment of enzyme. And when pH affects enzymes, positivity, negativity, then it affects on our body also. Now, if we look this one here, when it has more negative charge, then again here positive, again here is positive. That means isolated point to be aggregates. When I told less than 4 pH or 4 pH, it has more positive charge. When it has more positive charge, there is no negative charge to interact with the other protein, because both proteins have the positive charge. If we go higher, pH 11, then both proteins have the negative charge. And again we told negative does not interact with each other. And here, at isolated point, having a balanced negative and balanced positive charge, one can say protein aggregates because negative charge interacts with positive, positive charge interacts with others negative, and it precipitates. When it precipitates, then aggregation gets. And people are researchers, they are studying about the aggregation of proteins, and then they are making cell assembly from the enzyme. And not only this, so this is talking about protein, a polymer. People are binding this polymer with the protein via click chemistry, and they are getting amplified from that one. And those amplifiers, how it assembles in water, they are studying like this. That's why one can balance pH, one can modify this enzyme, and one can go for the assembly of the protein also. Now, if non-covalent interactions are so weak, why they are so important for biological system? We are telling covalent bond is stronger one, non-covalent is not that much stronger, it is weaker one. Then why it is using in the biological system? If we look this DNA with the negative charge, they repel from each other. If we put protein with the positive charge with this DNA, it interacts with each other, making a self-assembled material. We know that again charge interaction. That's why that is the basic. People are using both basics and employing here to study the self-assembled material. Now, if we put this enzyme around this enzyme, having again the salt, we have to use if we use excess salt, then what happens? Its effects on the enzyme, or if we have less salt, then what happens on the enzyme? Here, if we look, this is a negative charge, then the positive charge or interaction takes place with this negative one. And again, here is the balanced one outside of the protein, up at the longest place. Now, here, if salt is weak one, then interaction between two proteins, it takes place easily. But if the salt is strong one, then the interaction between these two proteins are very difficult, because again positive charge of protein interacts with these negative charges of the salt, and the negative protein, it interacts with the positive charges of the salt. That's why interaction between these two proteins are very difficult. Now this is the again natural system, DNA, protein, and here again charges play an important role. Here, this is non-covalent interaction. These are the muscle. What we are making now? Gene. Okay, how it functions? This is again the enzyme sites, and this is enzyme. It interacts with this muscle via the hydrogen bonding. Here I can show this is the bonding takes place in the muscle. Complex interaction. What is it? Expansion or contraction, what takes place on your muscle. It happens due to this hydrogen bonding. If these are covalently bonded, these two, then it is not possible. Then our muscle becomes like a steel. It will not do that. That's why these non-covalent interactions are most important things in our natural system. Supermolecular self-assembly, what we can do with these interactions. Now, this is a simple phospholipid molecules. One can synthesize such type of molecules in the laboratory. But synthesizing such type of vesicles in laboratory is very difficult by covalent interaction. When it is very difficult by synthesizing such covalent interaction vesicles, then if you look this one, here is positive, negative charges present. This is the hydrophobic tail is present. Then we know that hydrophobic interaction takes place. At the same time, this positive, negative charge interaction takes place. And such type of bilayer one can synthesize in the laboratory by non-covalent interaction as well as hydrophobic interaction. Here, particularly two, electrostatic interaction as well as hydrophobic interaction plays an important role to fabricate or to construct such type of vesicles in the laboratory. That means one can use these basic non-covalent interactions, plan the molecule, design the molecule, and look its assembly in the laboratory and how it assembles. What type of material we can synthesize from such interactions, one can see, and here, such simple molecule one can use and make a vesicle in the laboratory. If we go further, this is a TP molecule, recently it was published, and if we, here is the negative charges are present in this, and when we put such type of amplifying with this TP, then electrostatic interaction takes place, and such type of interaction again pi-pi bonding takes place. Pi-pi interaction takes place, or pi-pi stacking takes place, and one can synthesize such type of vesicles, and just recently it was published here. And if we put enzyme, this enzyme, it breaks this type of interaction, and again one can get our starting molecules. That means one can construct the system and one can disturb the system in the laboratory. Now this is a simple molecule. If we look in this molecule, there is no positive charge or no negative charge. Then also we can use such molecule for construction or fabrication of the self-assembled material. What we can do here, when we put this molecule, here is the pyrolytic system. We know that 5' interaction takes place via induced dipole interaction. Then here, if we look, this is the amide subunit, amide. And we know that this amide undergoes hydrogen bonding. That means here two interactions are involved: induced dipole, and amide hydrogen bonding. At the same time, third, hydrophobic interaction takes place. But when we put in water, most of the part is the hydrophobic one or isotope. In that case, it precipitates. When it precipitates, it makes particles. That means by using such type of, or by designing such type of molecule, one can get the particles in the laboratory process of water. If we put beta cyclotron or cyclotron in this system, yesterday I think Dallas told about beta cyclotron, its uses in the CTC and all those things. We know that this beta cyclotron interacts with this pyrene. When it interacts with this pyrene, it makes 5' interaction. Sorry, hydrophobic interaction. And then what happens? It goes inside this pyrene, goes inside this cyclotron, hydrophobic interaction. Then here again such type of particles one can convert into the nanotube. That means design simple molecule, convert it into particles. By changing or by using another medium, we can convert those particles into the nanotube. Such type of one can synthesize the nanotube. Then this is a nature produced by Gabriel Shaw from USA. These Iranian scientists were working in USA. What he did, he synthesized. He reported this is the first time. He synthesized this cyclic peptide, and he found that this cyclic peptide, in water, it interacts with each other. When it interacts with each other, then it makes a nanotube. How it makes nanotube? If we look this one, again hydrogen bonding, we have hydrogen present on the electronegativity atom. Then we have this oxygen. That means one molecule, NH, it interacts with the oxygen of the another molecule, and NH, it interacts with the oxygen of the another molecule. Such type of hydrogen bonding takes place, and one above the other, like this, it goes and make a nanotube. That means not only simple pyrolytic molecule, one can convert into the nanotube, but we can synthesize cyclic peptide and go to the nanotube. Further, what he did, he studied this self-assembled nanotube for antibacterial study, and still he is working in this. Then, Ida from Japan, what he did, he synthesized such amplifier. If you look this one, simple amplifier here. Here is the pi system. Here is again the hydrophobic and again the hydrophobic. That means every hydrophobic interaction, pi stacking, again in THF, they got the nanotube. And again THF water, they got the nanotube. That means, and it was published in Science, original Science. That means one can design a molecule, look its assembly and how it converts into the nanotube. That means here, simple molecule one can use for nanotube formation, cyclic peptide one can use for nanotube formation, and again such type of bigger amplifier one can use for the making nanotubes. Again, this is again the fluorine system. What these people did, they put this PP molecule with this fluorine, and they found in LTPS, this is again the amplifier. It converted into the such type of self-assembled material or nanoparticles. What happens? It self-assembles and makes a type of belt-like or sheet-like structures. And when they put this again amplifier, this belt one can convert into the nanoparticle. Or at the beginning, if they put this amplifier with this fluorine, they found that it already converted into the self-assembled particle. That means one can synthesize particles, seeds, nanotubes, again particles by using a simple molecules via non-polar interaction. If we look here, again it causes the pi interaction because this molecule, it goes inside the cavity here, this blue one, it interacts with this pi system and makes a self-assembled material. At the same time, here is again charges and it interacts with this charge and then it makes again the charge. That means charge-charge interaction as well as pi stacking takes place, and again here it interacts with each other and making a self-assembled material. This is a simple molecule. Just recently I picked up this one. And here, the position of nitrile group, it changes the self-assembled material or formation of the self-assembled material. That means not only its position as well as solvent also plays an important role. If we took this molecule or they took this molecule and studied its assembly in ethanol, again this second molecule with this nitrite, position with this one, and they found that in ethanol they make this type of chemical assembly. That means right-handed helix formation takes place. When this right-handed helix formation takes place at the same time, they took another molecule having this nitrite meta position. They studied its self-assembly in again ethanol. They found it makes a left-handed helix. That means change in solvent, change in position of the nitrogen. Simple molecule, it is not a difficult molecule. Then it changes the helicity. आपण म्हणतो ना right helix, left helix, helical form. असे फॉर्मेशनचे नॅनोस्ट्रक्चर can make in laboratory by changing the position as well as changing the solvent. Same molecule. In ethanol, it makes such type of assembly, whereas again in DMF, it makes reverse type of assembly. That means one can get right-handed, left-handed, depending on the solvents. Now these are the nanostructures they studied by State and all these things. Here they showed how it assembles and how it goes, how this is the pitch, how this pitch happens in this one. They took this one, this is the assembled material from this one. Now again, here they put the same system, last one, depending on ethanol, they got such type of assembly, in DMF they got such type of, and in KHF such type of. That means in ethanol they are getting this left-handed, and in DMF and KHF they are getting the right-handed. That means one can use the same molecule, change the conditions, and one can get two different type of nanostructures. This is the beauty of supermolecular. Now question is, apart from biological system, is it possible to use non-covalent structure in organic synthesis? Sir told organic synthesis, all green chemistry aspects and all these things. Is it possible to use supermolecular chemistry in synthesis? Answer is yes. People are working in this. Answer is yes. And now, again, non-covalent such as hydrogen bonding ion pairs, they play an important role to make a catalyst active of organic synthesis. Yesterday, Darasa told this synthesis of beta saturation, uses of beta saturation. Here I would like to tell, this is myself and Sheshina sir, we wrote one review in 2007 when we are the students. Just now, sir, students, they will file the patent. Like this, we are also interested to write something. At that time, Sheshina sir insisted me. We write one review on beta saturation. We don't know anything about beta saturation at that time. What we did the references, we collect the references, both of us, and we started writing at that time. I was also postdoc and he was also postdoc. And I think all our review, we have more than 70 citations also this one. Though we don't working in this field, then also we wrote the review at that time during our student days, and we got good citations, and people are using our review in synthesis, and we are not using. That means we are not working in synthesis field, then also we can do that. That's why I always say, sir, I like your students are reading 1500 papers, 1200 papers. It is most important thing. Again, I insist you, please read. That will make your life big fun. Here we follow this beta cyclohexane in this case. Without beta cyclohexane, this is structure is long here. This is anisole. Okay, and when without beta cyclohexane coordination of anisolide parallel position, it is not possible. But when they put this beta cyclohexane with this anisole and modified this beta cyclohexane OH by OCl, then they found that with CD they got 21.6 para substituted anisole. And this is happened because this inhibiting, it goes in the cavity of the cyclohexane, it makes interaction with the cyclohexane, system stabilizes. When system stabilizes, at that time, this para position is available for coordination, and which is not possible in the solution. And here the type of product formation takes place. And it was published in JAS in 1969. That means before I was born. Now in second system, what they did is again dichlorotoluene they used here for formulation, and they observed that now here particularly to get para product instead of alcohol meta, what they did they found that when they put this CCl4, this dichlorocarbon, they observed that this dichlorocarbon also goes inside the cavity of the beta circulation. When it goes inside the cavity of the beta circulation, at that time, what happens? This benzene or this phenol, this ring system, it goes outside of the cavity. That means ज्यावेळेस हा CCl4 मध्ये जायला चालू होतो कॅव्हिटीमध्ये त्यावेळेस हा बेंझिन न्यूक्लियस हा बाहेर यायला चालू होतो. त्यामुळे काय झालेलं आहे तर त्याला पोझिशन इज मोर अवेलेबल दॅन दॅट ऑफ आउटलाइन त्याला पोझिशन इन दिस सिस्टम अँड हियर फॉर्म्युलेशन आफ्टर साइड द त्याला पोझिशन that is 92%. Without beta this saturation they got 49:25 also parallel ratio, but in presence of this saturation they got the 92% of the formulation in this because it goes inside the cavity and it pushes it. That's why the portion is easily available to have the formulation. In second case again this cavity cation when they put and solution they carried out for this one. They observed that without this saturation hold to 53. That means this is the orthogonal ratio. But in presence of saturation they got 1:99%. That means one can use organic molecule for synthesis of organic compounds in the laboratory with efficient way and with more ratio sensitivity. Now this is a simple system. Ligand people are using this ligand catalyst for reactions. What they did, they modify, they put this ligand with this iridium. Here is the again urea system. If you look this one, here is urea system. When it has urea and when they put iridium here, what happens? Then this urea goes this side and here again interaction takes place. And this interaction means what they make here the compound, the substrate it makes hydrogen bonding and it is easily available for further reaction and they got again in conventional type they got 1.5, 1.5 and 0.86. This is the meta parallel ratio. But by using ligand they got 27, 16 and more than 30%. That means such type of ligand also useful for synthesizing such organic compounds. And it happens again due to the hydrogen bond. Here the hydrogen atom is present on this one. Here it interacts with this substrate and make easily available all its reaction. That's why hydrogen bonding also plays an important role. And here I can say one can use non-covalent interaction, make nanostructures, and one can use these compounds for the organic synthesis also. This beta circulation is very cheap one. You can use in your laboratory for your MSc projects also. Take any known reaction from such literature also, and you can use that one beta circulation